Low. Yeah. Oh, music. Music time. I forgot about music. It's music. Music, music, music. Music, music. Let me know if the music is a little too loud. Alright, more Kaggle time. I haven't done Kaggle in a while because I was so busy with a lot of other things, but I'm going to get back on track. It's Saturday, it's the weekend. I have time to myself and the kids are asleep. Just joking, I don't have any children. But I am actually very proud of us working on this Kaggle set because we successfully finished using logistic regression. It turns out that this dataset is 88% accurate in terms of using, in terms of predicting Pokemon using logistic regression. But is there another algorithm that can do something better? And I've actually kind of browsed other kernels, and I just did one algorithm. This guy just did like multiple algorithms using Python, TensorFlow, and or not TensorFlow, like all these multiple algorithms like decision tree, naive Bayes, all these classifiers like random forest, SVM, and what was another one? I forgot. But he did all that, like, and he just used a for loop to just like go through each algorithm, whereas I had to like just do one algorithm. I'm a little jelly, but at the same time, mine's a little bit more thorough than his. Just joking. Anyways, I'm joking about the whole thing, except the fact that he actually really did do all those algorithms, and his conclusion was that using random forest was the most accurate with 96% of accuracy predicting Pokemon battles. And I was like, what? Oh, that's kind of cool, man. I don't know how to do any of that. So what we're gonna do is probably implement another algorithm trying to predict Pokemon. I think what we're gonna do is probably figure out another classifier problem. One sec. So let's see here. Let us relax. Huh. So before we even start doing anything, I have to find out what I'm supposed to do now. We did the cross-validation, so we could do cross-validation techniques later if we have a different thing. But what I want to do is probably use LDA, linear discriminant analysis, because I don't know. It's commonly used as a dimensionality function technique in the pre-processing step. Oh, it's a dimensionality reduction technique. It's not really a machine learning, or it's a step for pattern classification and machine learning applications. Goals to project the. So it's not really the actual algorithm. It's just a pre-processing step. Okay, never mind. So there's principal component analysis, which I will cover later. LDA is something different. Oh, is this for linear? Linear transformation? Well, there, I don't think there's any linearity other than the fact that other than the fact there's a linear relationship between the log's odds of the dependent variable and independent variable. But does that mean the same thing if you apply it to linear discriminant analysis? Probably not. But let's see. Let's figure this shit out. Oh, this is really annoying. I'm gonna turn this thing off a little bit. We can do Bayes' rule, for sure. So, let's study a little bit. So you'll be able to work with Bayes' to compute conditional probabilities. The Bayes' rule is a 253-year-old concept. It's not 253 anymore. It'll probably be like 256 now. This set of instructions is like 3 years old. Man, I want some coffee, but I shouldn't.
You love most of us.
Its basic form can be stated in terms of events or set of occurrences, which we'll label A and B. Our goal is to obtain the conditional probability of A given B, and we can do so by using other probabilities, including opposite, so to speak. Conditional probabilities can compute it. Okay. Rare disease. Affects only 1 in 1,000 people. Person has disease. Okay, so we can like, instead of like saying person has disease, it would be like Pokemon, the first Pokemon one, right? Rare disease. Rare disease. That makes no sense. Yeah, no, it makes a lot of sense actually. Common example is to consider a test for rare diseases, such as a situation will allow us not only to discuss the Bayes rule, but also how observed versus predictive classifications are characterized. Huh. Yeah, I think we can definitely do Bayes rule. It'll say relabeling appropriate to context. We let D represent the event, person has a disease, which the person has a disease, and let P represent the test for the disease that is positive. So the event of the prediction is the probability of the test times of the event times the event over test of the event times event plus probability of the predicted times just the event. That's kind of like the classification matrix that we did for our Kaggle, though, for sure. All right. So in a way, we already did naive Bayes. Okay, so naive Bayes is just another assessment technique using certain classifications. So there's no point of learning this right now because we just did it. So this is a naive, I didn't know that though. I didn't know that. So this code here, the table using the threshold of 0.5, or it doesn't matter whatever threshold it is. This table is the naive Bayes confusion matrix. And that bottom, like top left, top right, bottom right stuff is the true false positive using the must-one specificity and the sensitivity stuff. I hate like running like this. That's like, I wish there was a way that I can just run all this at once. Is there a way to do that? Let's see here. So I didn't know this, but that was naive Bayes. Hey. I was just following the instructions, but now I'm kind of interested. All right. This is naive Bayes right here. This is false and true. Interesting. So but what am I missing though? So it's like negative and positive. This is basically what it is. True positive, false positive. This is such easy shit. It's literally like you just plug in the numbers. So if you want to know the true positive rates, it's always going to be on the right side, and then negative is always going to be on the left side. meaning that the left side is always going to be false positive and the right side is going to be true positives. So if people have classified no disease and it's negative, this is right, but they've claimed that it was a disease and it was negative and it was sign. That's false, right? So let's say for this one, for example, in our Kaggle thingy, 0 represents the people that actually lost. 1 represents the people that actually won, right? The first Pokemon that won, right? But this first column right here is that it's false. And then this one is that it's true. So it correctly defined that false is definitely false. But it incorrectly defined as that false was true, so it was a false positive. Whereas this is the true positive. They actually did so that what that means is that the first Pokemon, the algorithm, the logarithmic regression, correctly predicted 20,717 correct predictions if you use the testing data. Whereas they incorrectly predicted 2,884 as falses, you know? But it's really true. Or they incorrectly predicted it as true when it was really false. They corrected 20,717 true when it's really true, so that's a true positive. The true positive rate is this algorithm, so this thing divided by the total number of 2,080 plus 2,717, which is 88%, 87%, 80 to 88% basically. Whereas the person that when the algorithm corrected that they lost and they really did lose, that's good because it's 23740. But they lost, but then it's true. And that is wrong. But then the logarithm or the log regression predicted that it was true. 2,659 of those. But it's actually really false, so this was a false positive. Or a false negative. Okay, so let's redefine. So we got this thing right here. I'm actually learning as I go too. My mistake. This is a false negative. This is a true negative. This is false positive, and this is true positive. True positive right here, 1 true, because it turned into true. 1, if it's yes, then it's true. If it's true, then 2717 is true. If the logarithmic predicted that 2,884 said it was true, but in reality it was actually supposed to be false, it's a false positive right here. This is a false negative because a negative means that the negative in our context is that the first Pokemon lost. So 23,740 is a true negative because they correctly identified all the ones that are supposed to be negative false to 223740. And this is false negative. Negative and positive means predicted negatives and positives. What that means is that it's just completely relevant to the context of your thing. A negative for me, my context, is the Pokemon lost, the first Pokemon. The positive in my context is that the first Pokemon won. AKA right here. Okay. Alright, going on with this studying. That wasn't linear, that was naive Bayes prediction. I wonder who won the thing. Speaking of battles, I wonder who won, Khabib or McGregor? Oh, they haven't fought yet? When are they gonna fight? Oh, they haven't even fought yet? Oh, wow. Yeah, so we could probably use that. We could use LDA. Yeah, why not? We'll focus on continuous predictors. Predictors must be continuous predictors. Oh, never mind. We can't use continuous predictors because our predictors are not continuous. So linear so we need to have our predictors continuous? That's not good. We don't have continuous. Everything is just... Yeah, variable that has an infinite number of possible values. Yeah, we don't have that. Because Pokemon Kaggle, each continuous variables means that it has an infinite number of possible values. But none of our data have infinite possible values. None whatsoever. These are attributes that have finite from 0 to whatever. So it's more nominal? Is that what it is? Categorical variables. Continuous numerical variables? Oh yeah, all of our discrete variables. Yeah, so our values are all discrete. Yeah, we can't use continuous variables. There you go. Yeah, it's weird. Like all our predictors are discrete, meaning that we have to use classification models. Therefore, according to this bullshit, it is a classification algorithm, or it's a classification algorithm, but it has to use continuous predictors. That's weird, man. So ultimately we can't even use it anyways. It doesn't matter. Lipase levels are measured, not counted. So interesting. Alright, let's do this. LDA. Just to really make sure if we can't use this, then we're gonna skip it. Goal of discriminant: classify a response line into one of k groups or classes based on one or more continuous predictor variables. So we can't use LDA because none of our variables are continuous, they're discrete. Okay, skipping on. We can't use LDA because it only depends on continuous independent variables. We have none. Yeah, that's weird. I just now noticed that. This is discrete. Discrete is a measurement of counting, not continuous. It's like 1 through finite, not infinity. What is iteratively least? What does that mean? What is this? Oh wow. Oh, least squares, yeah. Well, least squares. There's so much about regression than categorical. It's very crazy. Alright. Now I know that we're just gonna move on to decision trees then. So let's learn about decision trees. Because I know that in the Pokemon dataset we can use decision trees, so that's our next objective. Because everything else just doesn't work. Naive Bayes is just a means of creating a table with a yes or no, with a true positive or true negatives, or false positives, false negatives. This is also a classification algorithm, yes, but it needs to use independent variables that are continuous, so that's irrelevant to our cause because our independent variables are discrete. Iteratively least reweighted least squares is only works for regression, linear regression, I think. I wonder what other types of regression it could be used. I'm kind of curious actually. It could be maybe for other regressions, meaning that it needs to have a continuous dependent variable, which is wrong. So decision trees, let's do this, baby girl. Method of supervised learning that can be used for either class or regression problems. That's fine. There are diagrams like this where the end of each line is called a leaf or a terminal node. And these represents the predictions. The places where one line splits into two are called internal nodes. And these divide up into predictor space. Each observation in this will either have age less than 3.5 or not. Each observer will either have equal to no or equal to some other value. Okay. This is especially good if you want to prove that's easy to interpret and communicate. Let's look at how to interpret this model, which deals with predicting whether a person has a heart disease. Okay, so that's a classification problem. Imagine that we're trying to predict the heart disease status of one particular person. We would start at the internal node at the very top of the tree called the root. This is labeled with a variable heart scan value normal. If the heart scan equals normal is true for this person, we move on to the left down this flowchart of sorts. If the heart scan equals normal as false, then we would move to the right. Is this a supervised technique? as a predictive model. So yeah, it's supervised for sure. I can see why a lot of people just skip to neural networks. That's why so many people don't really care. So it's interesting that you have to learn to understand decision trees and stuff like that, but it's hard to get accurate representation because there's a trade-off between interpretability and flexibility. Interpretability is that it just simplifies a little much so that it's easy to see what's going on, whereas if you use neural networks, it's kind of complicated. It's a little tough to interpret the model. It just works. Without really knowing why. Get it? Gotcha, fam. Decision trees are a method of supervised learning. Oh, just said it right there. They are especially good if you want a model that's easy to interpret and communicate. Let's look at how to interpret this model. I already read that part. So how do we build the tree model? We can do it by using a method called recursive binary splitting. Okay. Where we start by thinking about all of the data points as belonging to a single region, and then look for the best way to split that region based on a single variable. For example, in the dataset shown here, we might decide to draw a horizontal line at the height of 11.675 for the variable lower status population. It looks like it does a decent job of separating the points with high versus low medium home values that correspond to the tree with two terminal nodes, also called a stump. Apparently I'm learning random or decision tree now. Are we gonna learn random forest next? I just noticed that there is no such thing as random forest in my data mining. Well, that's a fine kettle of fish. Do we really not have random forest? Oh yeah, we do. So we do have tree-based models, right? Yeah, oh, never mind. Trees, forests, whatever. Gotcha, fan. You know, support vector machines is definitely a good classifier as well. Okay. We're using a supervised technique. Let's do random forest, baby. Partitioning. Is there a way? I would suspect that this Pokemon dataset is so perfect that the decision tree is the most perfect algorithm because it's easy and it's so perfectly divided, this thing. I see. Eventually I'll get there, but I'm really tired, so I'm gonna go now. But right now, at least we're making progress because we are now going to try to implement decision trees. Let's do this, baby. Alright, see you guys later.